All right. So this is going to be the presentation for section 6.4, which looks at number theory applications to the Gregorian calendar that we've been using since roughly 1600. So the goals and the learning targets of this section, and we're going to run through all this. Number one, we want to be able to use properties of congruence and the greatest integer function to determine the number of leap year days between 1600 and any given year after 1600. We want to be able to use properties of congruence and the greatest integer function to determine the weekday of March 1st for any year greater than or equal to 1600. We want to be able to use properties of congruence and the greatest integer function to determine the day of the week on which the first of each month of the year falls for any year greater than or equal to 1600. And lastly, and this is kind of really the culminating goal of the entire section, is given any date in history, past, present, or future, to be able to determine what day of the week that date fell on. For example, when was the Declaration of Independence signed? What day of the week was April 13th, 1902? Without having to go back and actually trace back a calendar, we can calculate this mathematically using some of the modular arithmetic and the theory behind the greatest integer function that we looked at in section 6.3. So those are the four main goals that we want to be able to take away from the section. A little bit of background information that we need for the remainder of the presentation and for the remainder of this section. So I'm just going to run through a few bullet points here. We're going to assume that each year starts in March. So March will be month 1, April will be month 2. That gets us through December being month 10, and we're going to consider January to be month 11 of the previous year, and month 12 would be February of the previous year. So January and February would be considered months 11 and 12 of year Y, even though in the typical Gregorian year that we're in right now, it would be considered year Y plus 1. So, and that's a little confusing. So I guess as a really basic example, if we were in February of 2022, that would be considered month 12 of 2021 for the algorithms that we're going to be looking at. So even though February is considered the second month of the year, we're going to be considering it month 12 of the previous year, just for our computations. The days of the week are going to be assigned 0 through 6 for Sunday through Saturday, respectively. So Sunday would be day 0, Monday would be day 1, so on and so forth until we get to Saturday being day 6. This allows us to work modulo 7. We're going to assume there's 365 days in a common year, March 1st being the first day of the year, February 28th being the last day of the year, day 365, and 366 days in a leap year. Leap years are defined as years that are divisible by 4, except for those marking centuries. And any century years will be considered leap years only if they are divisible by 400. Because 365 is congruent to 1 mod 7, that means that February 28th, so day 365 of the year, will always fall on the same weekday as the previous March 1st, which would have been the first day of that previous year. So February 28th and the previous March 1st will always fall on the same day. So that immediately implies that the next year's March 1st will always increase by 1 weekday than the previous March 1st, except in a leap year. So if it's a leap year, because of the congruence, 366 is congruent to 2 mod 7. During leap years, the next March 1st will always increase by 2 weekdays because the congruence is now 2 than the previous March 1st. So a little bit of background information we need. So this leads to our first congruence, which says that the weekday number, which we're going to call D sub Y, for March 1st of any year after 1600 will always satisfy the following congruence. So the congruence states that the March 1st of any year is congruent to the day of March 1st of 1600. So this corresponds to March 1st, the weekday number, that 0 through 6 notation we used before of 1600, plus the difference in the year number from 1600 plus L, where L represents the number of leap year days between March 1st, 1600 and March 1st of the year Y. So I guess the question becomes, we know the year number, we know 1600. How do we determine L? How do we determine the number of leap year days between March 1st of 1600 and March 1st of the current year that we want? So it's a 3-step process. First thing we do, step 1. we're going to count the number of years that are divisible by 4 past 1600, but less than or equal to the year that we're looking at. So this is going to tell us the number of leap years in general. Second thing we're going to do, we're going to deduct the number of century years, but then we have to remember some of those century years actually are leap years. So we have to add back in the number of century years that are leap years. And from the previous slide, we saw that means they have to be divisible by 400. So we have 3 computations that we need to do. Because of problem 2A of section 6.3, this was actually proven in the 6.3 presentation at the very end. We have a property of the greatest integer function, which says if we take any number and subtract an integer a, that will and take the greatest integer function, that will always be equivalent to the greatest integer function at that value minus a. So really we can break a out of the greatest integer function because it's an integer. So we're going to utilize that property to do some of these computations. So I guess first thing, step 1, we'll call these step 1, step 2, step 3. Let's calculate the number of years divisible by 4 between 1600 and the current year that we want, which we're calling capital Y. So what I'm going to do is take the greatest integer function of the difference in the number of years between 1600 and my current year, divide by 4, and then I'm going to round down in order to apply the greatest integer function. So if I split the fraction apart, this would give me y over 4 minus 1600 over 4, which is equal to y over 4 minus 400. And using this property 2a, 400 is an integer, so this reduces to the greatest integer function of y over 4 minus 400. Similarly, we can calculate the number of century years, which is going to be given by the difference in the year number in 1600 divided by 100, since the centuries are multiples of 100. Similar computation leads to y over 100 minus 16. And again, we can break the 16 out of the greatest integer function by property 2a. So here's result number 1, here's result number 2. Last but not least, we have to add back in the number of century years that are divisible by 400, since we got rid of them in step 2. So one more time, split the fraction up. This time we're dividing by 400, so this would be a 4. And using property 2a one more time, I get y over 400 greatest integer function minus 4. And so all we're really going to do is we're going to take the result from step 1, subtract the result from step 2, and then add back in this result from step 3. And so this allows us to obtain the following formula for the number of leap years. So we get y over 4 minus 400 minus, next. And now we're subtracting out y over 100 minus 16. That was the number of the years that were divisible by 100, the century years. And then we add back in the century years that were leap years, which was our y over 400 minus 4. Okay. And then doing a little bit of distributing and combining, this leads us to our following formula: y over 4 minus y over 100 plus y over 400. And then all of the constants here are going to combine. Minus 400 plus 16 and minus 4. If we do the math on that, that leaves us with minus 388 at the end. So this would be something to box, because we're going to need this. So we can use this. Let's say we wanted to find the number of leap years between 1600 and the year 1995. So in this case, I'm going to let capital Y be my year. So we're looking at 1995. And all we're going to do is we're going to substitute that in for Y in the formula right above. So I'm going to let, let's just use L like we have for the formula. Number of leap years. So I get 1995 over 4, greatest integer, minus 1995 over 100, greatest integer, plus greatest integer of 1995 over 400. And don't forget to subtract 388 at the end. Doing these computations, this is 498.75, greatest integer, minus 19.95, greatest integer, plus 4.9875, greatest integer, minus 388. And so everything is a floor function. So this next lowest integer would be 498. This one would be 19. The next one would be 4. And then we subtract 388. And doing the computations, we find that there are 95 leap years between 1600 and 1995. So just an example to see with numbers how that plays out. Using this result with congruence 1. So congruence 1 we had labeled previously. Let me go back and find it. Here was congruence 1. So what we can do now is we can actually substitute in our expression for L. So if we wanted to look at our calendar and figure out what day of the week did March 1st of 1600 fall on, we can actually solve backwards, because we know if we look at a calendar, we could go to March 1st, 1995 and see that that happened to fall on a Wednesday, which is why we're substituting into 3 over here. Okay. And so solving backwards, this was my year. This was my L value that we just substituted in. We can go backwards and find what day of the week March 1st of 1600 fell on. So this would be 3 is congruent to D sub 1600. What does this give me? 490 is what all of this adds up to. And we're working mod 7. So I get 3 is congruent to D sub 1600, and 490 is actually divisible by 7. 70 times 7 is 490. So this is just plus 0. And so what this tells us, it has the exact same remainder as the remainder from 1995. So since 1995 fell on a Wednesday, that tells us that March 1st of 1600 also happened to fall on a Wednesday. So that's a nice algorithm to have, because we don't want to have to go back and look at a calendar from all the way in 1600. None of us were there, right? I wasn't. Okay. So restating, we can now restate congruence 1 as congruence 2, because we now actually know the value of D 1600. So that's where this 3 is coming from right here. Rest of the formula stays the same. Now, we're working with pretty big values. Once we start getting to, 2022, or if I wanted to know somewhere in the very far future in the year 3000, what day would a particular, or what day of the week would a particular date fall on? I don't really want to have to be working mod 7 with something in the thousands. That starts to get a little bit tedious. So we can alternatively start expressing the year number modulo 7 using this expression. It's 100 times C plus Y, where C denotes the number of centuries. And since we're measuring from the year 1600, we would want C to be at least 16. And Y denotes the year number within that century. So it's always going to be at least 0 if it happens to fall on the century, but always less than 100, because otherwise the C value would just increase by 1. So really a couple of very basic examples. If we were looking at March 1st of 2022, here's my year. I could express Y, since March is the first month of that year. Remember, we're starting March as month 1. This would be 100 times 22 to give me the 2000. I'm sorry, 100 times 20, not 22. 100 times 20, and then I would add on 22 years for little y. So little y is the number of years past the century. Capital Y is the actual year number. So this would be a case of C equals 20 and Y equals 22. For January 1st of 2022, we could express Y. Now this one's sneakier, because remember, January 1st of 2022 would technically be month 11 of 2021. So this is really the year that we're looking at, because they specified a month. If they just called it 2022, I would do the same thing I did in the first bullet point. But since they're specifying that it's January of that year, I actually have to think about it as the 11th month of 2021. So I'm really going to do 100 times 20 and then add on 21. So my C in this case would be 20, but my little y would be 21 instead of 22. That'll only happen for January and February. Okay, so next up, we had an expression for L before. just to remind you, this was y over 4. This was from our last slide, minus y over, using capital Y over 100 plus capital Y over 400 minus that constant 388. Using our new expression for y, I'm going to outline this or highlight this in green. I'm going to substitute that expression, 100c plus little y, in for capital Y. So I get 100c plus little y over 4 minus 100c plus little y over 100 plus, what's my capital Y? 100c plus little y over 400 minus 388. And doing a little bit of simplifying here, splitting the fractions apart, this would give me 25c plus y over 4 minus, this would turn into c plus little y over 100 plus this would turn into c over 4 plus little y over 400 minus, don't forget about the little sneaky 388 at the end. Now, again, that property 2a that was presented in section 6.3 at the very end of the presentation is very useful. We know 25c is going to be an integer, so I can split this up using property 2a again. This would be 25c plus greatest integer function of y over 4. The next one I could do with a little distributing, this would be minus c minus greatest integer function of y over 100. I can't quite use that property on the third greatest integer function, but one thing I do know is that y over 400, since y is between 0 and 100, not including 100, I know that this is always going to be less than or equal to 100 over 400. So this is always going to be less than or equal to 1/4. So if I do a little scratch work off to the side here, coming over to the left-hand side, I know that that greatest integer function is going to be, so c over 4 plus y over 400 is going to be less than or equal to c over 4 plus 1/4. So that's going to be less than or equal to c plus 1 over 4. But this is also bounded below by greatest integer function of c over 4. And so this result right here is just going to be equal to c over 4, because how we do the greatest integer function is we're going to want to bound it from below, not above. So this would take on the same value as c over 4. I don't want to take the ceiling, I want to take the floor. So I would go to this one. And then I subtract my 388. Now, because the year, again, the year is between 0 and 100, this term is just going to go to 0, since the greatest integer function of a number less than 1 is going to be 0. So combining results here, we get 25c minus c would be 24c plus y over 4 plus c over 4 minus 388. And so this is an alternative expression that we can use to calculate the number of leap years. So congruence 2, if you look back at congruence 2, this would turn into dy is congruent to 3 plus, we would get y minus 1600. This was the original, and then I'll substitute in mod 7. So substituting in our expression here for y and for L that we just found, this would be d sub y is congruent to 3 plus 100c plus y minus 1600 plus, grab the expression that we just used, 24c plus y over 4 plus c over 4. I think I'll be able to fit it, minus 388, and we're working mod 7. And then if you do a little bit of reducing and you simplify the numbers mod 7, we end up with this expression. So this would be probably the simplest way of calculating March 1st of the day number of March 1st of any given year without having to actually plug in the year number from scratch. We could just plug in the number of centuries and the number of years past the century, and the numbers just work out to be a little bit smaller. So let's use congruence 3 here to do an example. Let's calculate the day of the week on which March 1st, 1990 would fall. So we'll call that, using our notation, this would be D sub 1990. So we need to know the century and the year past the century. So C in this case would be 19. And because we haven't reached January or February, little y in this case would just be 90, since we're 90 years past 1900. So D sub 1990 would be congruent to 3 minus 2 times 19 plus 90 plus greatest integer function of 19/4 plus greatest integer function of 90/4. With doing some algebra, this is 38, this is 90. 19/4 would give us 4.75, so this would be 4. 90 divided by 4 would be 22.5, so this would round down to 22. And so this would give us a grand total of, this comes out to something that's congruent to 4. Yeah, mod 7. Once you reduce mod 7. So thinking about Sunday was 0, Monday was 1, Tuesday was 2, Wednesday was 3. So therefore, this tells me that it would have been a Thursday on March 1st of 1990. Okay, so that helps us that gives us an algorithm for calculating March 1st of any given year. What if we wanted to know June 1st or August 1st, the first day of some month that wasn't March, December 1st? If we know what March 1st was, there's a nice clear-cut way that we can actually add on a specific algorithm to figure out how many extra days the first of each month would require, what that addition would be. And it stems from knowing that 30 is congruent to 2 mod 7. So that would mean a month that follows a 30-day month would advance its weekday count by 2. Whereas if you're in a 31-day month, like March, and you want to go to the next month, like April, 31 is congruent to 3 mod 7. So any month following a 31-day month is going to advance its weekday count by 3. Okay, so just coming from these two congruences right here. So let's just kind of fill in the blank here. What would that mean? June 1st will always be how many days more or how many days greater than the previous March 1st. So let's kind of maybe helps to sketch it out. March leads to April, leads to May, leads to June. And I'm going to use my, was it 30 days past September, something like that. March has 30. You can use that little phrase if that helps. There's 31 days in March, 30 days in April, 31 days in May. So if I want to know how many days gap there is between March 1st and June 1st, you know, so since March was a 31-day month, April 1st is always going to differ by 3 days past whatever March 1st was. So if March 1st was on a Thursday, that means April 1st would fall on a Sunday, 3 days past. Since April has 30 days to get to May, I would only add on 2 additional days. So if April 1st was on a Sunday, May 1st would happen to fall on a Tuesday, only be a 2-day gap. And then now we're back to a 3-day gap because May has 31 days going into June. So adding up from March 1st to June 1st, if I do these, this would be 3 plus 2 is 5 plus 3 is 8. But keep in mind, we're working mod 7 and 8 is congruent to 1 mod 7. So what that tells me is there would only be a 1 weekday difference between March 1st and June 1st. So if March 1st was on a Thursday, I know June 1st would happen to fall on a Friday. So this would always just be a 1 day greater than. And there is a chart in the textbook that tells you month by month what number to use. This formula is a lot, kind of a more compact way of expressing that without having to memorize that list. So the following expression produces the monthly increase that must be added to the day number of March 1st to arrive at the number of the first day of each month, 1 through 12 of any year Y. And so it's the greatest integer function of 2.6 times the month number minus 0.2. And then subtracting 2 outside of the greatest integer function. So let's try that with June real quick, just to make sure that that actually confirms what we found before. June would be, let's see, March is 1, April is 2, May is 3. So June would be m equals 4. So let's try this with m equals 4. 2.6 times 4 minus 0.2 minus 2 would be, what did I get from that? Here. 10.2, greatest integer, minus 2. So this would be 10 minus 2, which is 8. And we know 8 is congruent to 1 mod 7. So it still confirms it's a 1-day difference in the weekdays. You could try this with any month if you want. So then really, if I want to know the number of the first day of the nth month of any year y, all I'm going to do is take d sub y. So remember, this is the day number of March 1st of that year. And all the second piece is the number of additional days that we need to add on. So this is the number of additional, we'll call them weekdays to add on. And so we can use this. Let's say we wanted to figure out what day of the week was December 1st, 1990. So a couple things I'd want to know. What month is that? That would be month 10, since we're considering March to be month number 1. And we just figured out earlier, we know D sub 1990 from an earlier problem happened to fall on day number 4. It was a Thursday. So we're going to need to use that fact. This is from earlier. So if you hadn't done the earlier problem, you'd have to compute this first. Okay, so let's say I want to know December 1st, 1990. So I'm going to take 4 plus 2.6 times my month number, which is 10, minus 0.2, and then subtract 2 outside the greatest integer function. So I end up with 4 plus, if you do the math on this, this is 25.8 inside the greatest integer function minus 2. 4 plus round down floor function, 25 minus 2 gives me 27. And everything is modulo 7. So this would be congruent to 6 mod 7. And if we think of 6, Sunday was day 0. So 6 would therefore be almost a week later on Saturday. And there's that chart for reference on page 1, if you want to take a look at that. Okay. So last goal would be, we've done the first of every month. So what if I want the 13th day of the month or the 17th day of the month? Really any calendar date, past, present, or future after 1600, how do I know what day of the week it's going to fall on? And so every single algorithm has kind of been building. So this is our next one. If I want to determine the number W of day D, month M, and year capital Y, using the same expression from earlier, 100 times the century plus the years past the century, that's always going to be determined by the congruence D minus 1 plus D sub Y plus 2.6 M minus 0.2, greatest integer, minus 2. So let's break down the different pieces here. What do we have going on? So we got, find it. So this, remember, this was from the last algorithm. This was the number of the first day of month M. So whether it was a Monday, Tuesday, Wednesday, so on and so forth up to Saturday. And then, that would give me the first day of the month. Now I want to know if I add on the additional number of days. What if I want to get to March 13th? Then I'm always going to have to add on 1 less than the day number I want, because I already considered the first day. So I don't need to add on D, or I'm adding too much. So this is going to be the number of additional days. Number of additional days to get to, we'll call it day D, day little d. So using congruence 3 from earlier, we have D sub Y is congruent to 3 minus 2C plus little y plus C over 4 plus Y over 4. This is all mod 7. Okay, so substituting, we know this is congruence 3. W is congruent to D minus 1 plus, okay, D sub Y, all I'm doing is I'm substituting in this expression. So 3 minus 2C plus Y plus this guy, And then I'm going to add on the additional part at the end here. Go back to red, plus 2.6m minus 0.2 greatest integer function minus 2. Okay. You can see a lot of stuff cancels. So I have 3 minus 1 is 2, minus 2 is 0. So that stuff in green cancels out. And so I'm left with W is congruent to D plus 2.6m. And I'm just reordering a couple of these. You can keep them in the order they are if you'd like. Minus 0.2 greatest integer minus 2c plus y. And then don't forget the greatest integers on those fractions, c over 4 plus y over 4. So this is really the culminating result of this entire section. Is this is going to help us if we know the century number, the number of years past the century, and the day of the week that we're interested, or the day of the month that we're interested in, we can actually calculate if it's a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. And so this is the, I would say, the heart of the section. So we're going to draw a big heart around this theorem. Optional, but encouraged. So our theorem says the date with month M, day D, and year capital Y given by, there's our expression from earlier, 100C plus Y, where C is greater than or equal to 16 and 0 is less than or equal to Y is less than 100, has weekday number given by the expression I just mentioned. Okay. And again, we're assuming March is taken to be the first month of the year. So March is M equals 1. January is assumed to be month 11 of the previous year, and February is assumed to be month 12 of the previous year. So let's use this to calculate a couple days. I just picked a couple dates, some math dates, cheesy math dates, right? We're all math nerds, don't tell anybody. When was, and some of these, obviously you'd have access to a calendar for, they're more recent, but you could do this with dates. On some of the homework problems I suggested, you could do these with dates from the 1800s or the 1700s. The algorithm works out the same way. So I just picked some fun dates. Back in 2015, you might remember Pi Day of the century. It was 3/14/15. I still remember I was at my computer studying during undergrad, and I captured the moment with my phone. I took a picture of it. I even bought the t-shirt. I'm pretty sure I sent a Snapchat to my friends, and they told me, "You're a nerd." I said, "I know, I embraced that." Okay, Pi Day of the century. So when was it? What day of the week was it? Maybe you remember this, but let's confirm it. So I'm going to put my algorithm down here. Let's make a couple notes that we're going to need. We know we're in March, so I know M equals 1. Okay, what else do we know? March 14th, I know the day number is 14, and I know that I am looking at 2015. So my century number would be 20, and since it's not a January or a February, I don't have to do that subtraction with the year number. So little y is in fact going to be 15. We don't have to use 14. So using my algorithm, I'll write it out at least for the first one so we can see it. This would be from above. Let's write this out. It's D plus greatest integer 2.6m minus 0.2 minus 2c plus y plus c over 4 plus y over 4. And we're working, see if I can fit it here, mod 7. Okay. So let's see what we get. D is 14. So we're on the 14th day, March 14th, happy Pi Day, plus we get 2.6 times 1 minus 0.2. So we're going to get this whole thing right here will be 2.4, which greatest integer would be 2. Minus 2 times the century is 20. We are 15 years past the century point, 2015. Greatest integer of 15 over, oh, not 15. Century is 20, 20 over 4. The next one is the year number, 15 over 4. I'm just going to draw an arrow. We're still working mod 7. So let's see what we get. 14 plus 2 minus 40 plus 15. This would be the greatest integer function of 5 would just be 5. And 15/4 is 3.75. So the greatest integer would be 3. And so if you add this up, you get -1. And since we're working mod 7, 7 minus 1 would be 6. So what that tells me is March 14th, 2015, if we use our numbering system from page 1, this tells me it was a Saturday. And I do remember it was a weekend. Close your eyes and see if you can think back to what you were doing on that day. Okay. This one's more recent from this year. You might even, again, be able to predict based on the number here, but we had a Tuesday this year. It was all twos. It was February 22nd, 2022. And the spoiler alert, I guess, is this actually, the fun part was this actually did happen to fall on a Tuesday. Now we're going to use the algorithm and actually confirm that, but that was what was super cool about this day. I remember showing my students this. So let's confirm that it actually did fall on a Tuesday. So we would expect the answer to this should come out to W is congruent to 2. Since Sunday is 0, Monday is 1, Tuesday would be 2, mod 7. So we're trying to confirm that we get 2. So same algorithm, we're going to get W, let's see. In this one, let's label like we did last time. M is 12. As we're in the 12th month. Remember, March is month 1, so February would be month 12 of the previous year. We're on the 22nd day. And the century would be 20 since we're 2000s. However, remember, you're going to have to use little y as 21 since we're looking at it as the 12th month of the year 2021. So this would give me 22 plus greatest integer of 2.6 times 12 minus 0.2 minus 2 times 20 plus 21. And then we have our 2 greatest integer components at the end, 20 over 4 plus 21 over 4, arrow, mod 7. This thing in the greatest integer function at the beginning, I computed this to be a nice clean 31. So we're actually going to get 22. We don't have to do any rounding. 31 minus 40 plus 21 plus 5, and 21/4 is 5.25, which will round down to another 5 using the greatest integer function. So we get 44, which is congruent to 2 mod 7. And there we go. That confirms that Tuesday did happen to fall on a Tuesday. Okay. Last thing I think it's kind of interesting, and this was in the text, and I thought it would be worth describing in a little bit more detail. They reserved about a paragraph for it, but there was a couple computations I kind of wanted to walk through a little bit more detail to justify. There's the whole superstitious idea of Friday the 13th being bad luck. And so in the great words of Michael Scott, if you watch The Office, his quote was, "I'm not superstitious, but I am a little stitious." And that's always one of my favorite quotes from the show. I always thought it was funny. So the question really, and I mean, maybe you've never thought about this, or maybe you have, is does every year have a Friday the 13th? And so I guess make your prediction, and then underneath we're going to actually go through and see if this actually will always happen. Don't check a calendar. Just make your prediction based off what you think. Is every year guaranteed to have at least one Friday the 13th? Maybe more than one, but is there going to always be at least one? And so we can actually use the congruence that we established earlier. We had, remember, W was congruent to D. I'm going to write it one more time just so I can fill in a couple pieces here. 2.6M minus 0.2 minus 2C plus Y over 4. Nope. And Y over 4, C over 4. Doesn't matter which one I list first. I'll just do that. Okay. This is mod 7. So this is essentially asking, I want it to fall on a Friday. So that would mean I want W to be equal to 5. So that's where I'm substituting in this 5. And I want it to be the 13th day of the month. So I would want my day number to be 13. So that's where I'm substituting in 13. And then the rest of the congruence, I want to know, will this work no matter what capital Y I choose, no matter what century, no matter what little y? And therefore, kind of figuring out, is there a month where this is guaranteed to happen? And so really what it boils down to is looking at this component right here, because this is really the only component of the equation that depends on the month. So we want to know if all possible months or along those lines could allow this to happen. And so if we look at this, what I would encourage you to do is maybe pause the video for a minute. If depending on time, if time is low, you can keep going, but pause the video and try and fill out this table real quick. And see what you get for your value of the greatest integer portion of that equation for all 12 months, and then reduce your answer. I'm going to make a third column over here. Reduce it mod 7, because you might get something larger than 7. So if you have time, pause at least for a minute or two, see if you can get the values, and then I'm going to fill them in the table. So this would be March, April, May, June, July, August, September, October, December, January. Oh, I mixed up something. March, April, May, June, July, August, September, October, December. Oh, I skipped November. I don't know my months. Okay. Sorry to those of you who have a November birthday. December, January, February. Okay. So this gives me 2, 5, check year values as well, 7, 10, 12, 15, 18, 20, 23, 25, 28, and 31. And reducing mod 7, I get 2, 5, 0, 3, 5, 1, 4, 6, 2, 4, 0, 3. It looks like just a whole string of digits, but again, if you have time in class right now and you want to pause and chat with a neighbor, is there something interesting you see about any of the numbers in this pattern that could help you actually decide, is the Friday the 13th guaranteed? Something is sticking out to me here that actually allows you to conclude that there is guaranteed to be a Friday the 13th every single year. See if you can figure it out real quick. Okay, so if you had some time to talk, one thing to notice is if you look from May all the way to, oh, I don't want to cover those up, I want to highlight them. If you look from May all the way to November, you'll notice this is the only part of the sequence of numbers where you actually get every single number mod 7. So 0, 1, 2, 3, 4, 5, and 6, not in that particular order. But what that tells me is that every single time I come back up here for the months of May through August, or the months of May through November, 0, 1, 2, 3, 4, 5, and 6 are all going to appear one time, which means it's kind of like a permutation. If you plug those numbers in, add 13, and then add the remaining stuff, it's going to end up spitting out 5 at some point, right? If I put in 0 through 6 here, all numbers 0 through 6 are going to be guaranteed to pop out here at some point. So the interesting thing is, because of the fact that all 6 of those numbers pop up from May through November, means 5 is guaranteed to be an output for one of those months, meaning there's going to be a Friday the 13th guaranteed every year, some month between May and November. Maybe more than once. This portion here guarantees it happens, so I'm going to put guaranteed. Guaranteed May through November. Possibly January, February. Oh, now I'm thinking of the Gregorian calendar. Oops. March, April, and possibly December, January, February. That's going to depend on the year. And doing a little research online, I think what I saw is that there's always going to be at least one for this reason. And there's always going to be, I believe it was at most 3. So you won't have more than 3 in a year. So yes. Guaranteed every year, no matter the century, no matter the day number or the year number, every year, May through November. Oh, Microsoft Word is having an issue. Hang on a second. At least once. Okay. So let's just, let's answer the question then. So for this year, for 2022, when is there guaranteed to be a Friday the 13th? Don't take out your calendar. Let's see if we can actually figure this out. So really, we're trying to solve the congruence here. 5, that would be Friday. Day is 13 plus 2.6 m. I'm trying to solve for m. I want to know what month is it going to happen. Minus 0.2, minus 2 times 20, plus 22, plus 20. I'm just using the algorithm from earlier. 20 over 4 plus 22/4. If you go through some of the reduction on this, you'll end up with 5 is congruent to 13 plus 2.6 m minus 0.2 minus 40 plus 22 plus 5 plus 5. And so I get 5 is congruent to 5 plus 2.6 m minus 0.2. This is all mod 7. And so subtracting 5 from both sides, I want to find the m value that produces 0 on the left-hand side. And so you can try this with some trial and error. The only m value, actually, we can just go back to our table from this. The only m value that makes that happen, let's go back up top here. This is the one nice thing about having that table. The only time 0 actually popped up was in month 3, which is May. And it's going to be May. I don't know if anybody gets that reference. Actually, May started yesterday. So May 13th, 2022 will be a Friday the 13th. Hopefully that doesn't scare you. So that kind of concludes the thoughts from this section. That gets through all the learning targets and checkpoints that we had talked about. If you're looking for some extra practice, these are some similar examples to what I did. We got section 6.4 extra practice. I picked out some of the highlights. Another cheesy joke. This is kind of a fun one. You can determine the day of the week on which you were born, so everybody will get a different answer for that one. A lot of these are in the back of the textbook. You can check. I picked out, when did the San Francisco earthquake happen? When did the battleship Maine blow up? One thing I'll direct your attention to for this problem is, since we're dealing with February of 1898, just to be careful with your choice of little y in this case. Remember, February is considered to be month number 12 of the previous year. So I won't tell you the answer, but just to cue you in and make sure that you're thinking about that when you set that problem up. Likewise for number 5, we just did Friday the 13th for 2022. This problem is having you look at it for 2010. So you can check that one in the back. The only one I think I will walk through is number 5A, just because it's a slightly, I mean, we have all the concepts, but I think this one makes you think a little bit about what you're actually solving for. So it says for the year 2010, so we're looking at C equals 20, and we're looking at, well, let's see what Y is going to be based on the month that they tell us. It says, what calendar dates did Mondays occur? The calendar dates on which Mondays will occur in March. So since I'm dealing with M equals 1, I know I can let my year still be 2010. I don't have to think about it as 2009, since that's the start of the new year. Okay, so what I'm actually solving for here, the calendar dates, I want to know day numbers in the month. So I don't know D in this case. We've seen examples where we've solved for M, examples where we've solved for W. I wanted to do one at least where we solve for D. So we're still using the same congruence equation. W is congruent to D plus greatest integer 2.6M minus 0.2 minus 2C plus Y plus greatest integer C over 4 plus greatest integer Y over 4. Did you ever think this much math went into the calendar? I didn't. And so we can actually plug in. So we know it tells us also, it doesn't give us the value, so we kind of have to read into the problem, but it says on which Mondays will occur in March. So right away, I know my W value is going to be 1 if we use that table from the front page of the handout. So I'm just going to plug in and solve for D. I get 1 is congruent to D plus 2.6 times 1, we're in March, minus 0.2, 2 times 20 plus 10 plus 20 over 4. This is all mod 7, so I'm just going to keep writing or drawing an arrow to the mod 7, 10 fourths. So I get 1 is congruent to D plus 2. If you do the math on that, minus 40 plus 10 plus 5 plus, this comes out to 2.5, so this will be 2. And so we have 1 is congruent to D minus 21 mod 7. So we're solving the equation. D is congruent to 22 mod 7. And since 21 is divisible by 7, this is equivalent to solving D is congruent to 1 mod 7. So any day that's congruent to 1 mod 7 in that month is going to work. So really every multiple of 7 increased by 1. So don't forget about the sneaky case of D equals 1, because technically 7 does divide 1 minus 1. So March 1st will count. The next number would be 8, would be congruent to 1 mod 7. So March 8th. The next value of D that would work. So I'm just going to highlight so you can see it. This is D, this is D, this is D. The next one would be 15, since 14 is divisible by 7. So this would be 315. 21 is divisible by 7. So the next one would be the 22nd. And then last but not least, otherwise we're going to be into April at that point, would be the 29th, since 28 is divisible by 7. So we get 5 dates in March that happen to all fall on Mondays. Okay, so that'll conclude this section. If you have additional questions or any further questions for me or want clarification on anything, send me an email. I'm happy to go through and explain things in more detail or help out as needed. Thanks for listening.